Welcome to Chapter 1, Part 3 of The Air We Breathe, Chemistry in Context, 7th edition. We are continuing on and introducing chemical reactions and balancing simple chemical equations. Chemical reactions are everywhere. Look out! There's one over there. Oh, watch out! There's one over there. Um, there are actually literally thousands of reactions not only happening around us but also in our body. The picture on the left, you see methane, a hydrocarbon, burning or combusting in oxygen gas to produce heat energy to cook food. The picture on the right shows a sugar molecule, and it has the formula C6H12O6. When you add oxygen to sugar, or glucose in this case, you get CO2, water, and energy. It's a very similar reaction that happens in our bodies that happens when we combust methane to cook food. The manner in which the reaction occurs is, of course, somewhat differently in how that energy is harnessed. How do we know that we're observing a chemical reaction? Well, there are a few indicators that provide evidence a reaction has occurred. Color change is one of them. So if you bite into an apple and let it sit, it begins to brown. That is a reaction between the molecules called polyphenols in the apples and oxygen. And the reaction changes the structure of that molecule slightly, but enough that a color change occurs, and that compound is colored brown. And when you're dealing with water-based solutions, often, or combinations of different liquids, often when you see a precipitate or a cloudiness form in that solution, it's really something changing from a aqueous or liquid phase to a solid phase. And frequently when that does happen, a chemical reaction has taken place. The picture on the left here is looks like some hangover remedy. This whole slide actually looks like one big hangover remedy. You've got some tablets put into solution that are releasing gas, so they are undergoing some type of chemical reaction. And then the picture on the right, you have a gentleman sniffing something. Maybe it's coffee, who knows? Um, the women in the audience might not really care what he's smelling. But it is one aspect of chemical reactions that they can also give off odor molecules, or gases can be released that may or may not have smell. In general, in chemistry, you don't want to smell any reaction you do in lab because of that uncertainty of what you may be forming. There are only very certain select instances where you may be asked to smell a chemical reaction that is performed in the safety of a monitored and supervised laboratory setting. Temperature change is a common one. Often reactions that occur release heat. They can also absorb heat. Those are a little less common. But when you have a hand warming pack, if you've ever seen those little plastic packages that you kind of bend a piece of metal inside it or break and mix two compounds together and it warms, that's a chemical reaction. Also the change of the properties of the aqueous environment, if it's a water-based solution, if there's a change in acidity, that also implies that a reaction is taking place. So the main ideas in this section are that, okay, we know chemical reactions occur all around us. We need to be able to talk about those chemical reactions in a systematic fashion. So we've come up with this idea of the chemical equation. We've already talked about how our different atoms can be represented by different letters, the symbols, the element symbols on the periodic table. And what we're doing is we're showing how those atoms combine in order for a reaction to occur. For a reaction to occur, there are always bonds in the reactants breaking, or atoms must come apart in the reactant molecules. And then bonds must form in the products. So here on the left side, these are always considered our reactants, the compounds or molecules we start with. And on the right, we have our products. Another aspect about chemical equations is they are what called balanced. There must be the same number of atoms on the reactants, or left side, as products, or right side of the chemical equation. This has to do with a law of the universe called the law of conservation of mass, or matter. Atoms in chemistry, excluding nuclear chemistry, can't just appear or disappear. So in any chemical reaction, if you started with, say, one carbon atom, in the products, there must be one carbon atom. Now it may be attached to other elements, or the structure of the molecule may have rearranged, but there should only be one carbon atom. So that's why we are concerned with balancing chemical equations. And it really provides a recipe for the chemist to follow in terms of what's the ratio of, in this case, methane to oxygen that we need in order to make our products, our carbon dioxide and water. Why don't you take a moment and see and look, do we actually have the same number of atoms for each element on both sides of the equation? Well, the answer is no in that last slide, and we'll get into more how to solve that issue right now. So above me, above these molecules here, we have a carbon atom. Oxygen, remember, is red, and an oxygen atom, and then we have what looks like maybe CO2. So carbon, oxygen. Remember when we talk about oxygen in the environment, oxygen always occurs as a diatomic molecule. So oxygen is O2, and it forms carbon dioxide. So these are different representations. Here's like a spherical space filling. Here's our nomenclature expressing the chemical reaction that occurs. And here's our chemical equation showing the elemental symbols and how our product is formed, our recipe for the reaction. Now this is a very simple reaction. It's a 1 to 1 to 1 ratio. One carbon atom, one oxygen molecule forms one carbon dioxide molecule. In order for this to occur, these oxygen atoms must have split apart. A bond must have been broken between these two oxygens in order for them to attach to the carbon. There's one more bit of information here. There are these letters in parentheses next to our molecules or compound, and they indicate what phase the reactant or product is in during the reaction. Phase, or you may know of it as a state, a chemical state. So S refers to solid, L refers to liquid, G refers to gas, and AQ refers to an aqueous environment, meaning that substance is dissolved in water. So let's look at combustion reactions. Those always will involve oxygen as a reactant. Combustion reactions always involve oxygen as a reactant. So here we have nitrogen gas and oxygen gas forming nitrogen monoxide. But let's look at this reaction. Here we have 2 oxygen and 2 nitrogen, but there's only one of each in the products. So what we do is we put what are called coefficients, whole numbers, in front of our molecules or compounds in order to change the number of atoms in our chemical equation. We don't play with the subscripts. We don't say, oh, okay, there's one oxygen atom over here. I'm just going to go ahead and cross that 2 out, and I'll have balanced oxygen. You don't change your subscripts when balancing a chemical equation. So, oh, this is already done for me. Let's go to the next one. In order to balance this, we would need to add a 2 in front of the nitrogen monoxide here. Now we have 2 oxygens, 2 oxygens. This number applies to everything in the molecule or compound it's next to. So now we have 2 oxygens, 2 nitrogens, 2 oxygens, 2 nitrogens. And now we can, visually see that this equation is balanced. We have to start with 2 blue spheres here. We end up with 2 in our products, 2 red spheres here, 2 in our products. This first chemical equation would violate that law of conservation of matter. Atoms would have somehow disappeared, which we do not observe in the universe. There's a lecture activity in Chapter 1, Part 3 that I like because it gives you not only the opportunity to balance your chemical equation, but underneath that it has a nice particle level view. So really take a look at that particle level view when you're balancing. As you do more practice, you might find your own method that works for you in terms of keeping track of carbon and hydrogen atoms, or nitrogen, whatever molecules you're given on either side of the equation. One tip for that activity is sometimes if you have, say, an even number of oxygen atoms on the reactant side in an O2 molecule, so say you have just an O2 molecule over here, and if we're talking about combustion, combustion always produces CO2 and H2O. Notice how, let's go back to our methane. Okay. Notice how there are 3 oxygen atoms here. There's an odd number of oxygen atoms, and there's only one molecule, and its subscript gives it an even number of oxygen atoms. Not in this particular case I've drawn up here, but at times, in order to balance a system like this, you might need to multiply everything by 2 in order to make this an even number of oxygen atoms as well. So just keep that in mind when you're doing that activity. Let's review what we learned for this lecture. Matter is not destroyed or created. Atoms are merely rearranged in chemical reactions. So they cannot disappear. That's why we have to balance them in our chemical equations. These equations represent reactions. They are the shorthand notation for a reaction we're concerned with or observing. You have the same number of each type of atom on the left and right side of a chemical equation. In order to balance a chemical equation that's unbalanced, you change the coefficients, which are the whole numbers in front of the molecule. You cannot change the subscript of the chemical formulas. And here's another example. It looks like two carbon atoms combining with one oxygen molecule to make two molecules of carbon monoxide. But you see we start with two carbon atoms here, and we ended up with two. So this ends the third part of Chapter 1, covering Section 1.9 in the text. It's time to take a break so you feel a little more balanced. Ah, ah. Oh dear.